There is a robot on an M by N grid. The robot is initially located at the top left corner, grid 0, 0. Okay, here's the robot. The robot tries to move to the bottom right corner, grid M minus 1, N minus 1. The robot can only move either down or right at any point in time. Given two integers, M and N, return the number of possible unique paths that the robot can take to reach the bottom right corner. Test cases are generated so that the answer will be less than or equal to 2 times 10 to the power of 9. I remember doing a similar problem when I was studying discrete mathematics. So let's say we have a grid. We will start the rows and columns with 0. So 6 rows and 6 columns numbered from 0 to 5. So the robot starts at the top right corner. There are zero possible moves to get to the top right corner because that's where you start at. Sorry, I mean top left. Now the robot needs to go to the bottom right. It can either go right or it can either go down. So going to this particular square over here, the robot has to go right once. There's only one way to reach the square. And to reach this square, there's only one way, which is by going down once. Now for this square over here, you can go down from this square or go right from this square. Since we have one way to reach this square and one way to reach this square, then we have two ways to reach this square. Now let's focus on this square. Since there is only one way to reach this square, then reaching this square takes one more, which is by going right from this one. So that means there is only one way to reach this square, which is by going right from here. Now let's talk about this square. How many ways are there for reaching this particular square? Well, we can go right down, or we can go right down right, or we can go down right. So there are three ways to reach this square. Another way of solving this is that there are two ways of reaching this square. One way of reaching this square, since we have to move down from here or right from here, then we can just do 2 plus 1, which is 3. Now let's focus on this particular square. There's only one way to reach the square, which is by going right. Similarly, the same can be said for all of the rows and all of the columns. Since reaching this square, for example, takes only one path, which is down. Now let's focus on this particular square, which we can get here by going down from here or going right from here. And 2 plus 1 is 3. So there are three ways to reach the square. Continuing the same process, we can fill in all of the other squares with the exact same method. So 1, 2, 3, 4, 5, 6, and 6 plus 4, 10, 6 plus 4, 10. Then we have 15 over here, 15 over here, and then 20, 35, 21. And finally, we reach the end, which is 256, I think, 252. So there are 252 ways to reach this bottom left square. I'm going to repeat what I did again. So let's say we want to know how many ways there are to reach this square. We can go down, right. That's one way. Or we can go down, right, down. That's another way. And then, or we can go right, down. That's another way. So basically there are 5 ways. And one way we can calculate this is to get how many ways there are of reaching this square and get how many ways there are of reaching this square. Since reaching this square takes one move from both these squares, then we do 4 plus 1, which is 5. You may notice that these numbers look like they belong in the Pascal's triangle. I changed this to 1 because I think it would be easier to imagine this if the top left is 1. So if I write it down like this, 1, 1, 1, 1, 2, 1, and so on. So 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. This is basically the Pascal's triangle because by definition, the next number is like this plus this. I can redraw the Pascal's triangle and use combinations to find it. So for example, if I redraw the Pascal's triangle like so, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, then I can use combinations to find a particular value. So for example, let's say I want to find this one. I can start with 0. So 0, 1, 2, 3, 4. So row, choose, column. So for the value of row, it's 4, 0, 1, 2, 3, 4. And then column is like 0, 1, 2. So it's 4, choose 2, which is 6. Similarly, for the next one, if I want to find this particular value, I would do 5, choose 3, which is 10. So I searched online and there doesn't seem to be any C library with the combinatorics functions. So what I'm going to do is write a program for creating the m by n matrix and then summing up the diagonals. So we don't need the bottom half. I just need to sum the diagonals. Like I just need the top half and sum the diagonals till I get the bottom left corner. Okay, so I'm going to write the function over here and I have two test cases over here. First of all, I am going to make an array. Let's use malloc and m by n array. Malloc size of int times it by m and then times it by n. I think. Don't think I've ever created a 2D array with a malloc. I'll call it matrix int star matrix. Let's see. The top left of this matrix would be 1, right? Pointer, this also. And then we have m by n. It did me think. I think we're supposed to initialize a 2D matrix like this. It seems to be working fine, giving no error. Okay, we'll go with this for now. And let's write a for loop. Int I is 0 and then I is less than m. Let's do, m is what? The columns, right? Hold on. All right, looking at this, m seems to be the number of rows, right? Down, right? Yeah, m is the number of rows, n is the number of columns. N is columns, right? M row, but I don't think that matters. Columns. So we'll go through each row, r plus plus, then do a for loop again, this time for columns. And if we reach a diagonal, so for example, if actually no, never mind. I'll just add it over here. C is less than n. C is less than n. Okay, let's first do this. No, I think we should do the columns first. So what I'm thinking is we only want the diagonals, right? So if I draw another grid over here, we only want this, and then finally this, but we don't want this, right? So we calculate all the columns, and in the next loop, we don't start columns from the start. We started from here, started from 2. So we started from m, right? So rows, columns. See, I think I was right before. So we go through each column, but we start with m. But isn't there a lot of wasted space over here? I think I'll deal with that later. So then we do matrix. Matrix m, no, row, column, right? So the current row and the current column is like previous row and previous column, but we have an issue. But the thing is, how would we know? Hold on. Okay, looking at the corners again, you will notice that 2 over here is the double of this, 6 over here is the double of 3, 20 here is double of 10, 70 here is double of 35. So I think what we can do is calculate, we will first start with ones, and then we will do, for the diagonal, we do double of this, just 2, and then calculate the rest. And then similarly over here. And then for diagonal, we do double of 3, then calculate the rest, and 15. And for diagonal, we do double of 10, which is 20. I think that would make sense, right? Then the final answer is 35. Okay, so first we need to fill up all the ones. Let's see. Okay, so starting over here with all 0. C is 0, less than n. Yeah, mad. So the matrix 0, column is 1, right? And then we do m. Okay, let me think about this. We start with m. M is 0 over here. M is 1 over here. M1 C1 gives the column. M2 C2 gives not the column, the diagonal. M2 C2 gives the diagonal. M3 C3 gives the diagonal. Okay, let me think. So we should start with, okay, so this over here, R0 less than M. The row starts with 1. So the diagonal one, which is RR, is equal to the double of a matrix RR times 2, right? But it's the previous row, right? Also, I need to figure out the edge cases. But before that, R1 less than M. Let me think. So C, that means we have to start with m plus 1. For example, where r is equal to 1, we set this to 2 manually, and then in the loop starts over here with C is equal to 2. And then when the row is 2, the loop starts with 0, 1, 2. The loop starts with C is equal to 3. 2 is set manually, right? 2 is set manually, which is double of the previous row. Let me think. But what happens in the case where the columns is smaller than the rows? I think I will think about that later. Anyways, m plus 1, c less than n, c plus plus, c. So, no, this is wrong. This plus this, right? So, this plus this, right? That's the loop. And then we finally return mat m minus 1 n minus 1. Okay, let me reformat this. Would this cause an issue? What if there are more columns than rows? Okay, so first the program initializes all of this to 1 and then double of 1, 2. So this becomes 3. And then over here we have 3. Sorry, not 3. We have 6 over here. But hold on. Okay, how about this? What if we assume that the number of columns is always bigger? We just flip the grid, right? Because if this was vertical, the answer would have been the same. The answer would still be 36 if this grid was vertical than horizontal. I have an idea. So int rows is equal to m, int columns is equal to n. No, we take the bigger one. Is there a way to initialize a multiple? Never mind. Rows, columns. If m is bigger, then m is then the columns is set to that. You just always assume that the columns is bigger. Columns. Okay, is this good enough? Let me run it. Hopefully everything works well. Okay, there seems to be an error. I don't know what that was. Print d mat n minus 1 n minus 1. Okay, let me think about this. Int r c. I will initialize them over here. Number of columns minus 1. Okay, so what I'm thinking is R may not go all the way till the end, right? Like it will not go all the way till rows, or maybe it should actually. No, it's the columns which would not go all the way till rows. So C, I think I should see over here. Int R, I think like that. So what I'm thinking, row will definitely finish, right? Rows will definitely finish, but the columns, hold on a minute. No, I'm wrong about this. I think I should print the matrix as well. Okay, I think I will print the matrix. Okay, I think this should be good enough. Let me see. Okay, it wasn't good enough. Okay, let me see what the problem is. There seems to be a lot of garbage values for some reason. Okay, looking at the second example, for example, no, I shouldn't print the answer for now. Okay, looking at the second example where we have there are 3 columns and 2 rows, doing 1, 1, 1, and it's correctly calculating 2 over here, but it doesn't calculate second one where C, okay, let's see, C is not M plus 1, R plus 1. Okay, now let's see. It says 7, 28. It says 3 over here. 28 correct. Now how do is there a way to add 2? Add 2 over here. Let's do ans percentage D. Ans percentage D. I'm getting 28 and 3, which seems to be the correct answer. So let me see if my test case works. Okay, let me take all of this, put it here. I accidentally pressed Ctrl S and now it's trying to save. All right, let's run the test cases. Test cases seems to pass at 0 millisecond. Okay, I just submitted it. Hopefully it works. Okay, so let's see. Runtime beats 100%, but memory beats 20.31%. Okay, let me see if there's a way to improve memory. If I submit it again, what happens to the memory? Because the memory fluctuates a lot, right? No, memory is still horrible. I think one way to save space, if we assume that row is 1 less and we delete all of this. So we start with 2, 3, 4, 5. So let's delete all of this. So now there is 0, 1, 2. There are 3 rows. The first row is 0, the second row is 1, and the third row is 2. And the first row is like 2, 3, 4, 5. And we can reduce the column also by 1. So we can use this square instead. Okay, let's try that. So, let me think. Okay, what if we need to remove the base case where the column or the row is 1? So, we assume that columns has the bigger value, right? Yeah, so if the rows is 1, then we return 1, right? That is because if there's only one row, then it looks like this, and there's only one way to reach the end, which is by going right. Now, we assume the rest of the case. Rows, columns. Let me think. M is more than N. Columns has the bigger value. Okay, how about this? We do -1, -1, and -1, -1. And if rows is 0, then return 1. Rows, columns. C in the first case, we C is equal to 0. But we start with 2, right? C plus 2. We start with 2. We start with 2. 3, 4, 5. Yep. So 0, 0 has to over here. And the rest is the same, right? I don't think this was save space. I think this was save runtime. No, maybe the matrix would be smaller, right? Okay, let's see if the result is the same. Yeah, it still says beats 20.31%. Maybe I have to reduce the executable, or maybe not.